So hi everyone, and welcome to our 8th panel in the Future of Information Processing event series. My name is Dimitria Lee, and I am part of the German Informatics Society, which is helping IFIP celebrate its 60th anniversary this year by presenting a series of events that will look at what the future may hold for ICT. Our moderator for today is Philippe Cudre-Mauroux. Philippe is a full professor and the director of the Exascale Info Lab at the University of Freiburg in Switzerland. He received his PhD from the Swiss Federal Institute of Technology, EPFL, where he won both the doctorate award and the EPFL Press Mention in 2007. Before joining the University of Freiburg, he worked on information management infrastructures at IBM Watson, New York, at Microsoft Research Asia and Silicon Valley, and at MIT. He recently won the VeriSign Internet Infrastructures Award, a Swiss National Center and Research Award, a Google Faculty Research Award, as well as a €2 million grant from the European Research Council. His research interests are in next generation, big data management infrastructures for non-relational data, and artificial intelligence. And with this, I would like to hand over moderation to him.
Thanks a lot for the nice intro. Good evening, everyone. It's a real pleasure to be here. Let me share my screen. So welcome to this panel entitled Future Trends in Databases, from data science through artificial intelligence to quantum computing. As you've seen on the poster, we have 5 distinguished panelists tonight. You can see them all here. And basically, we'll have hopefully a nice discussion. So don't hesitate to chip in and to ask questions in the second part. Before starting this panel, let me just extremely briefly tell you about our group, right? The group that we are representing today. It's called the Working Group 2.6 on Databases. The group has actually some history, right? You can see on this slide that it was already established in '74. Wow. I didn't join at that time, but I joined some time ago, actually, like probably some 15 years ago or so. And we are a member of TC2, right? Software engineering. And currently, according to the latest statistics that I've seen on the website, we have 19 members and 9 observers. So we have the chair of the group tonight with us, Robert, from Potsdam University of Technology. We also have the vice chair, Paolo, who will be one of the panelists. And our secretary is Antonia Azzini from Sefriel of Milan. What do we do as a group? Well, we have a bunch of actually pretty, exciting activities. We've been organizing conferences. This is, for example, an image from one of the conferences we recently organized, SIMPDA, which was the Symposium on Data-Driven Process Discovery and Analysis. We publish papers. We publish joint papers, which is one of my favorite activities of the group, right? This one is not our last paper, but it's the second to last paper on big data semantics that we published in the Journal of Data Semantics 2-3 years ago. So that was fun. And thanks to Robert, who's been pushing seminars, we have this seminar series online. So we meet every month or so to discuss, basically research directions, latest results in terms of data management, data processing, data semantics. So that's basically it. For the group, right? This 2.6 group. By the way, here is Robert's email. If you would like to join our group, don't hesitate to send Robert an email. Again, I think it's a fairly interesting community if you are into data, data-driven AI, data semantics, etc. Okay, that's all in terms of speaking about the group. Let's now start with the panel itself. So here is the format of the panel. First, each panelist will basically have a short intro, about 5 minutes, to talk about the latest kind of research directions that she or he has been working on in terms of data semantics, databases, data science, AI, and quantum computing. So this will take about 25 minutes, and then we'll have a Q&A session where I will ask questions to the panelists, where we will have polls as well, and where I hope you will ask questions. So I'm looking forward to this. And without further ado, let's start with the first panelist. So Tiziana, can you share your screen? It's my pleasure to introduce Tiziana Catarci. You probably know her. She's a full professor in computer science and engineering at La Sapienza in Rome. She's the director of the Department of Computer Control Management and Engineering, and she's the editor-in-chief of the ACM Journal on Data and Information Quality. She's been recently working on AI ethics, and she won many awards. I will not cite them all, but basically, you know, just to cite a few recent awards, she has been including among the 100 Women in Science projects. She received the Levi-Montalcini Association Award for diffusion of scientific culture among young generation, and she was also included in the Inspiring 50 list. So Tiziana, without further ado, please go ahead.
Thank you, Philippe, for the introduction. And yeah, I will briefly talk exactly about data quality from a different point of view. So many people say that data is the new oil, since data is so important, in this specific time of creation of the digital age. But I would say that data are much more than oil, since are not a consuming resource. They are not going to disappear using them. On the contrary, they are growing and growing and growing, and they may be getting new importance and being interpreted in different ways and combined in different ways. So are really a very important resource, and it is even more important that they are of good quality. Now, which is the point of the quality? In addition to the traditional data quality dimensions, like completeness or timeliness or the other traditional dimensions that of course are very important, because if we want to base a lot of the digital revolution on the data analytics and on the availability of data, it is important that data are of good quality. But in addition, let me say that data are particularly important for machine learning. So everybody here in this panel perfectly know what machine learning is, so I would not introduce it, but let me say that since machine learning heavily relies on human created data that are the result of human processes and are annotated, cleaned, maybe manually by humans, they very likely will contain biases, conscious or unconscious biases, and the machine learning automation processes could amplify such biases, while we hope that the digital society would be more equal, more diverse, and have more social value than the previous one. This could not be the case because we risk to reproduce through data exactly the existing inequalities or discrimination, or even introduce new ones. So there is a tendency of talking about artificial intelligence for good. That is an artificial intelligence in which the technology, the algorithms are built taking into account the human-centric approach and the social value of the results. And in particular, but I will not enter in the details of this, I just want to mention what are called the social mind, the quality measures that in particular have to do with data quality. And as I said at the beginning, is a new interpretation of the concept of data quality. In particular, social-minded quality measures are measures that evaluate the effects of algorithms on the society on the basis of the degree to which they faithfully reflect the notions of ethics. So the result of an algorithm should not be influenced by attributes that are not relevant. Like you cannot give a credit to someone based on the gender, on the social provenance, on the ethnicity. Only the related attributes have to be taken into account. And in particular, in order to guarantee this social mind that design of the algorithms, it is important to have data that reflect the fairness as a data quality measure. So there are several definitions of fairness. Let me just mention 4 of them. The first one is individual-based fairness. Similar individuals must be treated in a similar way. Of course, you have to define the notion of similar on a case-by-case basis. So data do not have to contain biases about specific individuals, as well as they do not have to contain biases about groups. And this is a group-based fairness. So individuals are placed in groups based on the values of one or more of their protected attributes. Protected attributes are typically gender, religion, age, sexual orientation, ethnicity, and so on. And all groups must be treated equally. For instance, in terms of false positives and false negatives. Then data have to reflect the notion of fairness versus equality. It is not enough to have the same treatment for individuals. You need to get the same impact. And finally, diversity. One has to be sure that all the different types of entities are considered and represented in the data. So data have to be as much as possible diverse in terms of both input and output. And in this view of new dimensions for data, as well as we have the traditional data cleaning process, we may have a phase of data debiasing as a part of the data cleaning. And I think that I have concluded my 5 minutes. So thank you for the attention.
Super. Thank you so much, Tiziana, for this insight. Next short presentation will be by Monica Scanapieco. So Monica, if you can share your slides. Monica is currently the head of the Information and Application Architecture Division at the Italian National Institute of Statistics. And she's been working there since 2006. And she's been leading innovation projects. She earned her university degree in CS and her PhD from Sapienza Università di Roma. She is the author of many papers in data quality, privacy preservation, data integration, and she has been involved in several EU projects on data quality, on integration, open data, and big data. So, Monica, the floor is yours.
Thank you, Philippe. Thanks for this invitation and for giving me the opportunity to share my view. Currently, I work, as Philippe mentioned, at the Italian National Institute of Statistics, ISTAT. My view will be in the direction of showing you concretely that on one side, there is official statistics that is a sort of data factory. So for we as a database people is really a funny work to work at the National Institute of Statistics, because we really have the opportunity to work with data every day. And data science. So data science is something new for the official statistics, giving giving to official statistics a lot of perspectives and new issues. So the world where official statistics come from is a world in which there are survey data, that is data that are collected according to well-defined processes that have defined steps and are carried out in a production way. Together with the administrative data, so all data that we are used to collect at national level from the different organizations that provide to central statistical office their data. So for instance, in Italy, we have something like 200 surveys, and these surveys are either collected via questionnaires or are collected as input, let's say, administrative data. And I used to follow a very, let's say, defined process that is called the generic statistical business production process. So what happened in a new world in which there are not only survey data and administrative data, but there are also big data sources. This process that I briefly show in the previous slide is completely different. It looks much more complex at a glance. We have defined in Europe, together with the other National Statistical Institute, a big data reference architecture in which we, in a sense, have redefined all the production that we can do by using big data sources. But what are the specific issues that we have, and in relation to which we are putting in place several solutions? First of all, we have a paradigm shift with respect to the inference that we are used to have in producing information starting from data. This is because we are used to have a top-down perspective in which we have models and we have a design-based survey. And starting from this design, we are used to produce statistics. While in this new world with big data sources and data science methods, we are progressively introducing a bottom-up perspective, an algorithmic-based one. But these do need, as Tiziana Catarci already mentioned, a new quality framework. So we are actually in the phase in which we do need to revise properly the quality framework that we have and that is standardized at European level for producing our statistics. Because of course, official statistics need to respect very strict quality rules. So quality for us is particularly important. The second important investment that we are doing is on accessing data from these big data sources, many of which are privately held data. And this means from, in terms of investment, investing on privacy enhancing technology for acquiring this data or having access to them. We are already very well equipped with respect to output privacy with the statistical disclosure control methods, but we have to invest more on input privacy, so on methods for accessing this kind of source in a privacy preserving way, as well as on synthetic data generation, which is something very much important for us as well. Last but not least, we are used to produce statistics from sources that we can govern. When we access to privately held data sources, we need to produce statistics that are trusted, and building this trust concept in terms of quality, privacy, transparency, and ethics is something new for us as well. I think I can stop here. Thank you very much.
Thank you so much, Monica. Okay, let's go directly to our third panelist, Oscar Romero. So, Oscar, please share your screen while I introduce you briefly. So, Oscar is a professor at the Universitat Politécnica de Catalunya, UPC, and he's a member of the Database Technologies and Information Management Research Group. At UPC, he also coordinates the Erasmus Mundus BDMA, that's the Masters in Big Data Management and Analytics, and also the local Data Science Master. His research focuses on automation of the complete cycle of data management for inexperienced users with no or little technical knowledge, primarily focusing on the design and optimization of evolving and complex data ecosystems. So, Oscar, the floor is yours.
Thank you, Philippe. Thank you for the invitation. So we'll focus on the role of databases and data management for data science. And I will start quickly debriefing how it was in the past, how it used to be when we performed data analysis, where databases, and mostly relational databases back to then, played an important role. They were the cornerstone of the data analysis because they governed the data that they were serving to different layers of analysis. In these layers, we could have something traditional like data warehousing with the multidimensional modeling and their OLAP workloads, but then as well query and reporting, which were tools not that much into data warehousing or traditional multidimensional modeling, but in other formats like, for example, Splunk or similar tools. Ad hoc querying and ad hoc applications where you had a problem that did not really fit any of the shelf tools that you had in the market and had to create your own solutions, either tools that connected via JDBC to the database, extracted data and perform ad hoc transformations, or just online queries that an analyst may want to issue to the database to explore or to check data quality or whatever at a certain moment, right? But then we had another kind of usage where the data was not fully devoted in the database. It's when analytical tools came into play. I'm talking like, for example, SAS, SAS or R, where typically the connection of data was via dump files that you just dump it out of the database and then load it into the analytical tool where the analysis happened. But in general, the databases were and are the main drivers, right, to manage data. So from ingestion, storage, model, processing, and querying, even if we had this small disruption with the connection with analytical tools where we were dumping files. No? So things have just get more complex with modern data analysis of the so-called data science. Now things look much more complex. And here is, I'm depicting what we call the data management backbone. This backbone basically is serving data for analytical purposes. And now this looks much more complex than a single database, right? So we have the sources that somehow are ingested in the landing zone. This landing zone prepares the data. And then we have other zones where the data transits through. And basically these zones separate concerns, right? So we are doing different transformations at each step, just with the overall objective to reach to the expectation zone is where data is exposed and where user or external tools can use it for their analytical purposes. So just briefly, formatted zone typically is where we homogenize syntactically the data that may come from different and heterogeneous sources. The trusted zone where data quality typically comes into play to try to homogenize the data with traditional data quality processes. And then in the exploitation zone is when you already have integrated and performed data quality issues over integrated data and exposing it, typically in 3 different data models. We typically talk about relations, data frames, and tensors, which are the 3 typical data models that almost all data analysis require. And here we can just plug external tools. And if you realize this subsumes more or less the categories that I had before of query and reporting, OLAP, and ad hoc querying or ad hoc applications, because notebooks are now a fancy way to have these ad hoc ways to query data and process it and manipulate it in our own way, right? There is still the issue with the dumping files, right? But I will address it in the next slide. What I want to realize now is that this is much more complex than a database, and we still need a governance layer. This governance layer basically keeps track of what is happening throughout the system, or this data management backbone. Basically, we have different metadata artifacts that basically monitor the system, what transformations have been applied. This kind of information, this tracing is required to later do some interesting things like traceability or explainability, which are now hot topics and have already been mentioned. Also to know the data quality processes applied to data, etc. So in that way, we can trace basically everything that has happened in a single source of truth, which is a data governance layer. So then from here on, what would substitute to replace the traditional data analysis and off-the-shelf analysis is what we call the data analysis backbone. Here we connect to the exploitation zone, this source of truth where all the data is exposed from the system. And then here, then the data scientists can create their own analytical sandboxes that are nothing else than views or subset of the data exposed. And between these 2 layers, we have what we call when data meets models, because in the analytical sandbox, you still have variables, while in the other one, you have features, which is what the models consume, right? So here in these arrows, still you have further data preparation, further transformations, but these transformations are specific for the data analysis that you want to transform, while the data quality in the main data management backbone is generic, and you know that it's going to apply for whatever analysis you are going to do later. And here as well, we need to generate the training data sets and validation data sets that are required to train and validate models, and eventually, after you iterate many times here and you are satisfied with the model, deploy one of them. But the important thing here is that still here, with the difference with the previous backbone is this repeats for each data analysis, while the data management backbone needs to be unique for the organization. So the data source or the data exposure needs to be unique. There should be a unique source of truth, while then from there on, you can just do different data analytical pipelines for your analytical requirements. And yet here, we also need a data governance layer. So this backbone also needs to be governed. So we need to know what variables have been chosen to generate what features, what preparation rules or transformations have happened there, how the models have been trained with which training data sets, which validation data sets, with hyperparameters specification, and which were the performance metrics attached to this training. So, and from this all, the most important thing is that this data governance should not stay in the data management, but should also bypass throughout the data analysis. And this is one of the main challenges that we have nowadays. There should be a common governance of the whole ecosystem just to enable hot topics like traceability, data lineage, explainability, or collaborative analysis. This common governance, the way to do it nowadays, and this kind of a de facto agreement, is via knowledge graphs. Knowledge graphs are very flexible and easy to model, and then it's an easy way to just create different artifacts and simply link them. And the other big challenge we have nowadays is that we should be dealing with the whole ecosystem as a single DBMS, because in the end, all these 2 backbones and with their governance map to what was a database management system in the past. We had a single software. Now we have a lot of softwares that are orchestrated to generate a very complex ecosystem. But if we want to welcome data engineering good practices into data science, we need a single source of truth, both for code and data. Otherwise, we harness sharing and reusage. And also, we need to operationalize and automate these processes, the so famous nowadays data ops or machine learning ops, that lead in the end to facilitate or generate faster cycles to deliver, but also global optimization throughout the different stages. And with this, I would finish my part.
Thank you so much, Oscar. Very exciting topics from my perspective. Let's move on with Paolo Ceravolo. He's an associate professor in the University of Milan. You might know him. He was actually the chair of this group for quite some years, and now I think Paolo is vice chair. His research interests include data representation and integration, process monitoring, process mining, empirical software engineering, and machine learning. He has published many research papers on those topics, more than 150 papers actually. And he also has been involved in many international funded projects and in innovative startups. Paolo, the floor is yours.
Thank you so much, Philippe. So I'm sharing here our paper on big data semantics because I think many of the notions that we are presenting are included there. And, very important notion was already introduced by the previous speakers. I try to elaborate from it. So we have seen that today databases must be conceived as pipeline of interconnected data management steps. And of course, artificial intelligence, data quality play an important role in this pipeline. For example, artificial intelligence can be a tool we use in order to improve the efficiency or the automation of this pipeline, for example, for optimizing the queries that we want to execute, for learning new metadata that we are going to use in the management procedures. But artificial intelligence can also be a service that benefit from the availability of organized steps that prepare data or prepare processing activities and so on. So, however, in this context, as it was very well presented before by Oscar, we have this kind of complex pipelines that must be somehow standardized. No? So standardization is a big challenge today because, of course, standardization defines the best practice and defines the interfaces. Is about interfaces between technologies, yes, of course, but is also, maybe more importantly, interfaces with regulations, norms, specifications. You can think about the GDPR, or you can think about the new EU Data Governance Act that is now in draft. But we also have the Digital Service Act, the Digital Markets Act. These acts aim at encouraging greater reuse of data in the public and private sector. For example, they require that the condition that allow the reuse of data must be public, or that the public bodies cannot enter in exclusive agreements with other bodies for their data. On this, let's say, is the point of view of a public institution like the European Union. On the other side, we have companies. No? For example, e-commerce companies warned the EU that B2B data sharing is essential for business. For example, for optimizing the processes of company or in order to improve the customer experience. So according to their point of view, data sharing should be only voluntary. So how can you conciliate these different views, no? For example, on data sharing? For many computer scientists, a possible solution is thinking about smart contracts. Smart contracts use blockchain technologies in order to write, if-then conditions that can automatically activate the clauses of a contract. No? For example, if my fly is delaying over a specific limit, the reimbursement is automatically executed. But this kind of smart contract can be easy when you have well specified and possibly universal reference values, like the time or the economical values that are exchanged. So in this case, it's quite easy to write if-then condition. If you need to model something like understanding if a data set that can match with other data based on combinatorics, so this data set can provide market advantages to a competitor, or could trigger network effects that are positive for my business, you understand that it's much more complicated to model this using if-then conditions. So I think an important point to stress is before arriving to smart contracts, there are stages we still have to follow. And for example, in our joint paper here, Big Data Semantics, we discussed some of these issues and emerging ideas. Representing data is, of course, very important using schemata and metadata, but it's not enough today. We need to introduce standards for representing the data pipelines, not this operation that we want to apply on data and the outputs that are produced in order to verify, for example, the quality. And can we guarantee that the databases that we are adopting for training a model are balanced and are not biased and so on? No? This is something that also is related to temporal validity or a reference population that must be considered. So what I would like to stress is that standardization has its pre-requirements, like representation is one. Being able to represent data pipeline is essential. Of course, we need machine-readable representation. We also have another pre-requirement that is about having shared vocabularies. So we need to be able to define shared representation to be used. But another very important point is about certificates. Now, how can we measure a specific property of, for example, artificial intelligence technologies or data to be shared, or for example, data integrity, or the fact that the database is balanced? So this, I think, is a very important challenge to be considered now. And when all these stuff, so representation, certifications, and shared vocabulary will be in place, then we could start to think about having a smart contract that could be executing this kind of data sharing in partially automated way. So my idea was to put this point into discussion, not the importance of having certification, because each certification method that you want to propose should be accurately tailored on the needs and on the properties that you want to certify. Thank you.
Excellent. Thank you so much, Paolo. Let's switch to our last panelist, last but not least, Sven Groppe. If you can, Sven, share your screen while I introduce you. So Sven is a professor at the University of Lübeck. He got grants in various exciting technical topics like semantic web databases, FPGA acceleration, semantic Internet of Things, GPU and APU acceleration of main memory databases, and more recently also on COVID-19 knowledge graphs. He was the chair of the Semantics Big Data Workshop series twice, and also was a chair recently of the Big Data in Emergent Distributed Environments. He published over 100 peer-reviewed papers in his domains of interest, including in semantic web, query processing and optimization, cloud computing, GPU acceleration, FPGAs, peer-to-peer network, and visual query languages. So Sven, the floor is yours.
Yeah, thank you, Philippe. Besides a very basic introduction to quantum computing, I will try to provide some feeling about what you can do and what you cannot do with quantum computing. So quantum computers utilize the phenomena of quantum mechanics, which are the underlying principles of light and matter at the atomic and subatomic scale for computation. The principles of quantum mechanics are very different to experiences of our daily life. For example, according to some models in physics, electrons exist here and there at different locations at the same time, and are at one of the location with some certain probability when measuring the location. In my opinion, quantum computers can be seen as hardware accelerators like GPUs and FPGAs. Quantum computers are not suitable for every task in databases, but for those that are basically mathematical optimization problems. We will see this also on one of the next slides. So there are two main types of quantum computers. Universal quantum computers use quantum logic gates arranged in a circuit to do computation, and the measurement, which is also called observation, assigns then the observed variable to a single value, which is the result of the computation. Quantum annealing, on the other hand, can basically do the same as simulated annealing, but after generating the formula to be optimized in the pre-processing phase, the global minimum is determined with some ones in constant time in few milliseconds. We now consider the more general universal quantum computer. In classical systems, you operate with bits, you all know this, having two states 0 and 1. But with quantum computers, you operate with the linear combination of the two states 0 and 1, which is called superposition. And they are also called qubits. There are quantum counterparts for logic gates, like the NOT operation in form of an inverter. For example, the quantum logic gate, Pauli X gate, inverts the basic states 0 and 1, but also superpositions by exchanging the probability for the basic states. Like logic gates can be arranged to a digital circuit, quantum logic gates can be arranged in a quantum circuit. In this example, we see a full adder and its quantum counterpart, where you can process also superpositions, not only basic quantum states, considering also in G and tangent qubits. For example, in the last line of this table of in and outputs right here, after applying the C0 gate, measuring A will be 0 and B will be 1, or A will be 1 and B will be 0, such that the sum will be 1 and the carry bit will be always 0 in any case. So if we look at the timeline of quantum computers, there seems to be an exponential growth in the number of qubits supported by the quantum computers, especially considering leading technology companies like Google and IBM, which promise 1,000 qubits and behind in the coming years for universal quantum computers. IBM unveiled just last week the universal quantum computer with the currently most supported number of qubits with 127 qubits. Besides these leading technologies or technology companies, we should have an eye on startups like Quantum Brilliance, which develops room temperature quantum computers fitting in a server rack and promises support of about 50 qubits at room temperature in the near future. This kind of quantum computers come along with an attractive price. Then they might be used in medium companies and organizations, also e.g. for speeding up databases, at least according to my opinion. If we now consider the potential for speed up, then we see that there are many quantum algorithms, like with super polynomial speed up, i.e. that is a speed up, which is exponential or almost exponential, you could say. And many provide polynomial speed up, in most times quadratic or almost quadratic speed up. Most quantum algorithms with superpolynomial speed up are based on quantum Fourier transforms, which is a quantum analog of the inverse discrete Fourier transform. The most prominent example for superpolynomial speed up is Shor's algorithms for factoring integers in polynomial time, which triggered research for post-quantum cryptography. The most prominent example for polynomial speed up is Groover search, where you can find one solution X such that a given black box function determines true with quadratic speed up to classical implementations. Groover search is the basis for many other algorithms, applying exhaustive searches for finding a solution like it often occurs in mathematical optimization problems and also in databases. We can now identify the potential of applying quantum computing for database optimizations and see that, e.g., basic classical algorithms used in query optimizations like dynamic programming, reinforcement learning, random work, genetic algorithms, and so on have already a quantum counterpart, which can directly replace the classical approaches. And most times it has almost quadratic speed up to classical approaches. So yeah, research seems to be nearly done. Not applied in databases, but it looks already quite straightforward. But there are still some open challenges for quantum database optimizations, where you have to evaluate the quantum counterparts for their suitability to speed up databases, for example. Furthermore, the approaches can be further developed to consume less qubits by combining quantum algorithms with classical algorithms. We could determine what should be the properties of a quantum computer. That means number of qubits, latencies of gates, and so on to achieve certain speed ups. We will start with a project in the very near future, so in the beginning of next year, dealing with these open challenges quite in more detail. I hope there will be good research results coming out. Any collaborations are welcome. Thank you very much.
Thank you so much, Sven. Very exciting topics. Wow. So we covered already quite a bit of ground, from biases and social use of AI to database systems to machine learning pipelines. Where is the database? And finally, quantum computing. So now it's time to open up a bit the debate. So don't hesitate to write in the chat if you have any questions. I hope we'll have many. I will start immediately with one first question to our panelists. I would like to come back to this database issue and AI, right? To me, it's a bit surprising how poor the kind of data management tools that are used for AI, basically they are not really being developed, right, those tools. And it seems that a database system is not exactly used by AI machine learning researchers to go ahead with their projects. So what is your opinion on this? Is database management not useful for AI and machine learning development? Is it too complex? Is it simply not fitting the kind of tensors that the AI researchers are using? What is the problem between the lack of usage of database systems and basically those machine learning pipelines? Monica, please go ahead. Oh, Monica, then Oscar.
I think Oscar was before me.
Oh, sorry. Why don't you start, and then Oscar, I'm sure, will add some interesting points.
Okay. So from my point of view, I do agree that database tools are really not enough today for managing a data science pipeline. And one concrete example that I would like to illustrate is related to provenance. When I say we need to build trust for our final users, one way for building this trust dimension for our final users of statistical information is to have a transparent pipeline in managing this data. And this can be built manually. So we do have complete sectors that build this pipeline manually, like in Excel files or something like that. And having proper tools for managing provenance in data transformation that could result in a full data lineage from the raw data to the disseminated data would greatly help, just as an example.
I think no, this is a great point. I fully support that. Right, we should be working as a group on this, I suppose. Oscar, I'm sure you have lots to say about this point.
Yeah, no, I also agree that this is an interesting point. I think that the difficulty is that now the ecosystem is more complex and the current tools are not fit to be used right away. So we need to adapt them or just try to use techniques or good habits we learned from data management in the past in this new era or in new ecosystems. From my point of view, the basis is there, but the tools in production are not, right? So what I think is that in the next years, we will just see a bloom of tools that we already have, that they are trying to tackle this problem and trying to tackle provenance, lineage, or even explainability, which is another issue that also appears naturally in these systems. But I think still there is a way to go because there are a lot of tools that are proprietary and used by companies in-house that they are popular, but they are not that we can use right away in our production lines. So what I think is missing is this kind of flexible and adaptable tools. That there are quite a few. I think Databricks, for example, has a very nice ecosystem, but still there is a lot of room to satisfy what Monica was saying. This is still not there, even if it's a nice ecosystem. So I think it's a matter of going further, and I do agree that it would be a nice topic to work on this.
Excellent, thank you so much. Paolo wants to add something. Paolo, please go ahead. Oh, you're muted.
Sorry, thank you. I think what was mentioned is really relevant. So probably the concept, the notions to be applied are exactly the notion that was already developed by the database community in the past, but the way we have to deliver this notion is completely different. So somehow the systems are not ready. I would like to propose an example that could be of inspiration, in my opinion. Look at Netflix. No, the reason of the success of Netflix, of course, is related to the production, is related to recommended system, but is also a lot related to the quality of the streaming that Netflix is providing. Usually when you decide to watch your movie, you easily can start watching it. And many other platforms look, for example, to DAZN or even Telegram and WhatsApp are not able to reach this kind of quality. What's the reason? Because Netflix invests a lot on developing its own CDN servers that are delivering the content close to the users. They invested 1 billion, I think, in this technology, and it was a 10-year investment that they did. So maybe the key is a little bit in this direction. So being able to deliver the data to the user according to his needs. So we have seen that there are a lot of stages that could be required in order to consume some data within a artificial intelligence technology. Sometimes this is simply required in order to test something. And for example, Oscar was mentioned the idea of playground, or sandbox, this kind of notions. So probably if we could be able to prepare the data according to the need and deliver the data to users, think also about access control or maybe other stuff like this. This could help a lot in being more effective in delivering data.
Excellent. Thanks a lot for those points. We also have a couple of surveys and polls actually prepared for everyone, right? So Demetria, could you perhaps launch the first poll? It's about DevOps. Yeah, so, you know, basically it's about data ops and ML ops, right? I guess many of you have heard about those concepts. You know, the idea is to basically use some kind of systematic way of developing machine learning models, right? A bit in a database system way, kind of. So everyone talks about it, but it seems to me that it's mostly Google and Amazon who are using such systems and such basically pipelines, right? So please vote. Have you basically, heard, have you used data ops, ML ops for deploying and developing models, or is it mostly, Google who does that? Please vote. It seems that the hosts and panelists cannot vote, which is fine. Let's wait for the participants to vote a bit. So, okay, I guess most of you could take part in this poll. So can we get the results? How is it working? Okay, that's what I thought, right? So basically it's still, I guess those kind of systematic ways of trading, of deploying models, it's really the big companies which can use it, and it's not really the smaller, like the universities, the SMEs, the EU companies which can do it. That's very interesting, I think. Yeah, I think we should really work as a group on empowering users in that sense. And I'm sure that data management, data systems, they have a role to play. Anyway, let's switch gears. I would like then to come back a bit to the human aspect, right? Tiziana especially talked a bit about it. So it's still a bit unclear to me what will be the role of humans in the future, right? When we talk about data science, when we talk about models. So are we just here to create labels? Are we just here, to create data and potentially to then, train models? Or what's the story in terms of how should basically humans and data-driven models interact in the future? Do you have any insight? Tiziana, yeah.
Yeah, well, hopefully we would not just create labels. Actually, let me spend just 2 words against the new kind of jobs like this, in which, it's like the slaves in the chains, production chains of 2 or 3 centuries ago. You have people just labeling data, especially in certain countries, let me say. And that's a real one of the problems that exist in the new jobs, what is called the new jobs originated by the technological revolution. But coming back to the original question, I do think that humans will always need to be in the loop. So you cannot just rely on machines, because first of all attempts have been big failures. All completely automatic machine learning systems trying to decide who to introduce in a health program, health recovery program, or giving money or hiring people without any human in the loop have shown to be sort of a failure. But in particular, these tools should be seen, in my opinion, as really something used to augment the human capabilities. So they can do what we don't know how to do, and easily. but humans still can do much better a lot of things. So in my opinion, this is the future is really trying to better interconnect humans and machines and to create a virtuous circle. This, at least in the future, that we can foresee. Of course, we don't know what will happen in 100 years, but what we can foresee, that's my view.
Thanks a lot, Tiziana. Yeah, augmented humans and virtual circles. I can agree with that. Yeah, it sounds like, you know, a future which would be perhaps better than what we have now. Actually, Florent Cedes is asking a related question in the chat. We are often asked about biases and ethical issues. How can we help to fix such issues? Actually, yeah, I have a bit the same question myself, right? How can we basically try to minimize biases in those models? Do you have any of you any input?
Well, if I can add something else, okay. Minimizing biases is still a research area. There is no recipe, not yet. It's not that you get a set of guidelines and it's done. However, there are recommendations on how either to treat the data to be used or to build something that is unbiased or bias-free by design. So there are particular recommendations and guidelines that are, however, still very experimental. Then, you know, you have a lot of these ethics committee and the self-regulation. That's another story. But I think from a scientific and technical point of view, one may try to adopt the techniques that have been already designed, being conscious that are not final ones, so are really attempts.
Yeah, makes total sense. I think Paolo wants to add something. Paolo, please go ahead. Oh, you are muted.
Sorry. Yeah. So of course, what Tiziana is saying is very relevant. I would like to point out there is also another side, that is some people are doing research into the direction of verifying the properties of machine learning algorithms, looking at them as a black box. So you don't know how the algorithm was trained, and you want to verify if some properties are supported by the algorithm or not. So basically, the idea is to challenge the algorithm using specific data that you know are distributed, organized in a way in order to see which output the algorithm will provide you. And this link with the idea of certifying some pipelines, artificial intelligence pipeline that I mentioned before.
Excellent. Yeah, thanks a lot. Anyone wants to add? Oh, perhaps Monica.
Yeah, I think that a very promising direction in this respect is to build training set and benchmarks in a shared way. I think this is something that we are really looking from a practical point of view to achieve, because it's really hard to put in place full pipelines that can be proved as ethical and that can be proved as explainable, and the quality and certifying the quality of this pipeline is really hard. But when you start from the beginning, from data and from benchmark to do in a shared way, this is for sure a very good starting point.
Yeah, Oscar.
Yeah, just to add that I think that that's why it's very important to have a single source of truth about data, because then is when you can trace and you can just look at the quality of the training data sets and the validation data sets in my opinion, I think that companies are doing some very basic mistakes, and sometimes they do not even profile the data that they are going to use. And something as simple as simply profiling data and keeping track of these profiles to understand what kind of data they have, what kind of variables, it's just a small step but it can help. And many times, in my experience, it's not even done.
Yeah, no, absolutely. Thanks a lot. I think, we could obviously spend hours talking on those topics, but I would like to switch gears again because time flies. Let's talk just a bit about quantum, right? Since quantum computing was also on the title of this panel. So it's not a topic I'm familiar with really, but hopefully we have Sven and perhaps other panelists who know a bit about this. Let's start with a quick survey, right? With a quick poll. So we have a second poll. So Demetria, if you can show this second survey, it's about renting such a computer, right? Because it seems that now, for example, IBM lets you basically rent such a computer. So how much would you be willing to basically pay, right? How much money would your company spend for renting a quantum computer for speeding up relational databases? So please click on an amount of money to understand a bit how how interested our attendees are in terms of quantum computing and data crunching, basically. It seems that they are still pretty expensive, right? Those quantum computing, but hopefully the costs will go down. Okay, let's wait another few seconds and then perhaps we can see the results.
People still seem to be answering, so
oh, I see.
I'll just hold it on for another.
I'm too fast, sorry. Yeah, I guess right now could be pretty expensive to play around with those big toys, but probably the cost will be drastically going down once they are ready.
Here, I'll share it now.
Oh, so not too much, it seems, at this point, huh? 50 euro per month. I'm not sure we will revolutionize data processing with this. So Sven, perhaps can you comment on those results and what's your opinion? How much would you pay for quantum computers today?
So for me personally, I don't have so much money at all on my private pocket. But anyway, there are some numbers. For example, IBM Quantum System 1 in Ening. Yeah, you have to, or Germany paid, I think, 40 million for it. And yeah, you can rent it in 1 month exclusively, something a little bit above 10,000 euros. So, so two would nearly would be interested in renting the system right here, but you have a lot of free offers already. So if you only run 1 or 2 single programs, you can go to the internet, go to the cloud, run it completely for free, try it out. But if you want to do it on a professional basis, it's another thing. You know, there are also, for example, offers the first minute is for free or something like that.
Sure, makes sense.
You know? And so the technology, yeah, really becomes suitable to do really some things. But of course, if you do your regularly, then you have to simulate all the things. You know, if you want to do steadily, do quantum computing, develop programs for it, test it, then you first run a lot of simulations. And afterwards, you try it on a real machine, maybe if you have some connections, if you are in the yeah, IBM program or something like that, you can apply for it. So there are already some developments right here, and they already offer a lot of things to, yeah, to universities, companies, interested people. So it's really the thing where it seems to be that it becomes now stable.
Interesting, yeah.
From my observation, but Anyway, the price is still a problem.
Absolutely. So I guess, you know, no one can predict the future, but let me ask everyone on the panel. So what's your bet in terms of quantum computers? When will they be mainstream, basically? Is it going to be like, you know, if we hear the news from Google and IBM, it's going to be in a few years? I'm not sure I'm that optimistic personally, right? Could be a few decades, could be never, actually. So anyone wants to make some, you know, suggestions, some prediction about when will quantum computing be mainstream and replace some of the current IT infrastructure that we have? Sven, you have to tell us a number.
Okay, yeah, it's a thing that single quantum computers are already here and there on the world, you know. But I think it's when it becomes mainstream that is really the point, that this will take some time, and I think it will not be the Google and IBM quantum computers which you have to freeze down to the minimum degree, something like that.
I hope not.
Will be really that it will be the room temperature quantum computers, where maybe you don't get so many qubits, you know. There are already some startups, Quantum Brilliance, there's also another one, and so on. If there will be the breakthrough, so in the moment they have something like 5 qubits, it's not much. It's still limited. It's a toy, you know, but if it comes then to 50, 100 qubits in 5-10 years, something like that, if they can really achieve it, then is the point where maybe you can buy it in a server rack, and then so the 5 qubits are also fitting in a server rack in the moment, and then really maybe medium-sized companies can afford it and can buy it instead of a GPU system. So
Robert, I think, has a number to give us. Robert, what's your feeling?
I have a question.
Oh, even better. Go ahead.
Yeah, well, I don't know almost anything on quantum computing, but the issue is whether it fits this movement of green computing, and if whether it will not be banned in the future because of high energy consumption. That's
good question.
Yeah, it depends on if you have to freeze down it, as I said, or just have a light laser and diamonds, and then it works. I think then the energy cost will be much lower, and it's really that you need some technology change. I think IBM and Google go the wrong path with freezing it down. You can have many qubits with it, but it will not be for the mainstream. It will be for big research projects, maybe big research ideas, approaches, something to develop medicine against cancer or whatever. But it will be not that all small companies can buy it. And so that's the point. And yeah, of course, there's a strong competition with GPUs for. Anyway, you see the development, it becomes cheaper and cheaper and cheaper. So it will be also hard for quantum computers, you know?
Makes sense, yeah. Tiziana.
Well, I know almost nothing about quantum computing, but I recently was at a seminar by one of our colleagues from the physics school here, because they mainly work on quantum computing. And well, I had the great expectations, but then my feeling was that they are far away. So it's something like, you know, neural networks were invented in the 40s. And you may remember the expert systems of the 80s. I mean, the ideas were there, but something was still missing. Maybe technology, maybe something else, I don't know. So my feeling was that we had still to wait a lot of years to see a result. Of course, I may be wrong, but this was the feeling, at least given by the speaker also. Yeah, thanks a lot, Tiziana. Yeah, that's also my feeling, but who knows, right? It might be faster than we think. So I see that Demetria is appearing. Do we have time for one final question, Demetria, or should we close now?
Since it's being recorded, I figure you can kind of go ahead, and if people need to leave, that's fine. And if they want to catch up, they can watch the recording, perhaps. Sounds good. So let me ask one very quick question to wrap up, or to end this panel. It's a question that I received as well. So it's about all this CPU or GPU or quantum capacity that we have and which is not used, right? Right now, most of our computers, they have many cores, many GPUs. They're getting increasingly complex and powerful, but most of those cycles are not used. So could we actually make use of all this like idle power for something interesting, perhaps data-driven? Does anyone has an idea who could revolutionize the world? Anyone? I know it's a hard question, right? But what could we do with all those CPU cycles? Sven?
Yeah, sure. We can optimize in the background data distribution, have some common tasks in research which we download from somewhere, like in the past where you... Like
SETI, right?
Yeah, SETI, for example. There are also other, I think, searching for medicine or something like that. There are also other websites where you can install some program for it. I think there are a lot of opportunities regarding this aspect. And because we now can parallelize much more, we can make maybe now, for example, running queries all in parallel and see which is the fastest. We can do stupid things.
I see.
With all this computing power. But of
Absolutely.
course, it consumes energy, and then the climate change and so on. So maybe it's better to let the CPU sleep. That is another question right here.
Yeah, that's a good point. I know that, guess what? The CPU consumes less power, obviously, if you don't use all the cores, right? Okay, any final, idea in this context? Oh, Paolo wants to, the final word is to Paolo. Please go ahead, Paolo.
Oh, my comment is that, of course, I also think that one trend will be reducing the consumption of energy, but we should also consider that one trend maybe we will start using more our GPUs in the context of the metaverse, virtual reality, augmented reality, that I think will be a trend.
Yeah. No, I totally agree with that. Thanks a lot. I think we really have to close down the panel now, right? We are a bit over time. Thank you so much to all our panelists. Thank you to Robert. And I give the floor now to Demetria for the final word.
Thank you, Philippe, and thank you so much for your lovely moderation. And on behalf of the German Informatics Society and on behalf of the IFIP Events Coordination Committee, I'd like to say thank you also to our panelists and to the organizers and to all the participants. Thank you for staying around even as we went a little bit over time. If you want to see the recording of this talk and to learn more about upcoming events, you can visit ifip.org/jubilee60, and also make sure that you follow IFIP on Twitter and LinkedIn so that you don't miss the other exciting events and activities that we have planned. So yeah, thank you. Have a lovely morning, afternoon, evening, wherever you're calling in from. And again, thank you for such a lovely conversation among the panelists. Goodbye.
Thank you. Bye-bye.
Thanks, everyone.
Thank you.
Bye-bye.